AI generates this incredibly human-like text. It's super tempting to just compare it to our own biological brains. But they're completely different beasts. Your brain? It runs amazingly efficiently on about 20 watts of power. Think of it like a dim, energy-saving light bulb, right? It just runs smoothly on the calories from your lunch. AI, on the other hand, requires megawatts of continuous energy. It relies entirely on raw electrical power surging across thousands of interconnected chips. If the power grid blinks for even a fraction of a second, the AI stops instantly. It reverts right back to cold metal and plastic. Let's move to and see how this builds. To really trace where all this electricity is going, we kind of need to zoom way out from your laptop and step inside a sprawling AI data center. And listen, do not think of these places as just boring digital warehouses storing internet files. No, imagine them as massive power stations. They are highly engineered modern fortresses designed for one main thing: to safely route river-like currents of electricity directly into specialized hardware. The entire architecture of these massive buildings is literally dictated by power distribution. So, inside these giant power stations are thousands upon thousands of GPUs, or graphics processing units. Now, you probably already know these are the heavy lifting brains of the AI world. They were chosen specifically because they can handle the intensely complex, simultaneous math that these large language models need. Their parallel processing architecture makes them absolutely perfect for artificial intelligence. But, that exact same design is what makes them so incredibly power hungry. They're built to process massive data sets all at exactly the same time, which basically means they have to pull down huge amounts of electrical current. Now, what's really interesting about this is that to truly understand this massive power draw, we actually have to shrink things down to the microscopic scale. Inside every single one of those thousands of GPUs are billions of tiny components. Billions. We are talking about a staggering volume of electronic activity happening all at once. The massive macro power demand of the whole data center, that's really just the cumulative result of billions of these microscopic actions happening together. And those tiny components, they're called transistors. We generally know they act as tiny electronic switches, controlling the flow of electricity to process information, kind of like a light switch. But the real magic trick of modern computing isn't the transistor itself, it's the sheer mind-bending scale of the whole operation. By channeling raw electricity through billions of these microscopic gates, turning them on and off in unimaginably complex patterns, the hardware is physically processing the data needed to actually understand your prompt. So, intelligence, in this context anyway, is literally just highly organized electrical switching. Think about the quick life cycle of your prompt. You ask a question, electricity surges into the data center. Billions of transistors flip in perfect synchronized unison, and bam, an intelligent response is spit right back to your screen. What's truly incredible here is that this massive physical undertaking, billions of distinct microactions, calculating probability and language, it all happens in just fractions of a second. It is, quite literally, lightning transformed into logic. But as you might guess, you can't have billions of tiny physical switches firing at lightning speed without a pretty severe physical consequence. And that consequence is heat. The sheer electrical friction generated by this level of continuous computing produces an extreme amount of thermal energy. In fact, if it were left unchecked, this hardware would literally melt itself into slag in a matter of moments. The laws of thermodynamics, they definitely don't take a break just because the math happens to be digital. So this brings us to one of the absolute hardest engineering challenges in the AI space right now: thermal management. Surviving that intense heat requires massive industrial-scale cooling systems. And we aren't just talking about, slapping bigger fans on a computer. We're talking about giant heat sinks, heavily pressurized airflow management, and incredibly complex liquid cooling networks. They are absolutely critical to the operation. Honestly, delivering the power to the chips is really only half the battle. Stopping that exact same power from incinerating the entire facility, well, that's the other half. And this brilliantly illustrates a much broader point. But to really lock in how this entire invisible ecosystem operates, let's map it onto something highly visible and familiar. Let's use an electric car. This analogy completely cuts through all the technical jargon and highlights exactly how dependent the digital world is on the physical one. Okay, so think of the AI software, those incredibly sophisticated algorithms, as the driver who's making the decisions and steering the whole system. Then, the heavy lifting GPUs, those are the motor, right? They translate the driver's commands into actual physical work. The massive data sets the AI trained on, they provide the road for our car to drive on. But what about the electricity? Well, that is the essential fuel. Every single component here is vital, for sure, but without fuel, the entire system is completely paralyzed. I mean, a beautiful car on a perfect road goes absolutely nowhere with an empty battery.
So the crucial point is this: no electricity means no movement, no computation, and absolutely no AI. The intelligence you see on your screen isn't magic. It is an unbelievable feat of modern electrical engineering, and it is tethered directly and permanently to the global power grid. Every brilliant line of code generated ultimately relies on a physical turbine spinning somewhere out there in the real world. Which really leaves us with a critical, undeniable question. As we race to build infinitely larger and more complex AI models, they are going to demand exponentially more energy. Behind every single digital innovation lies a very real, very heavy physical cost. So, the future of AI isn't just a software problem. Where in the world are we going to find the clean, reliable electricity required to actually power it? Thank you so much for joining me for this explainer, and remember, always keep questioning the technology around you.